Welcome to my talk about Onion, Hexagonal, and all the other architectural buzzwords you know, and how we mix all these things together. In the beginning, when humans started to write programs, and back then they were called programs, not applications, they were really small because they were on punch cards. And even after programs, they were really small because we just didn't have the tools like AI to produce mass amounts of source code. So, and when things are small, they are easy to understand. But over time, our programs grew bigger and bigger and bigger, and we needed some ideas to keep them understandable and maintainable. And one of the first ideas was that we should separate things by concerns. And then, I don't know who, someone came up with the idea, yeah, let's make UI, business, and persistence. And first I have to do a little bit of a disclaimer, because I'm going to use a lot of different terms, and every term has at least three meanings. The initial meaning by the inventor, like in the initial blog post or in the initial book he or she wrote about the topic. And when an idea gets a little bit of traction, the inventor typically adapts the idea to more scenarios, makes it more general, improves it. And when an idea really gets into the mainstream and the whole community comes along and all the tool vendors, they typically change the meaning of a term quite dramatically. As an example, I'm using BDD, Behavioral Driven Development. It started out with Dan North inventing BDD because he thought developers don't like tests. So let's replace the word test with behavior. So instead of test-driven development, we have behavioral-driven development. And that got some traction, and he improved it. Yeah, we can use BDD to talk to domain experts, to make some specifications and make some automated testing from there. And then the whole community came along, and nowadays it's just Gherkin. More or less. So if you have a different understanding in terminology, maybe that's the reason that there are three meanings. So back to our classical layering. I'm sure you have seen a picture like that. UI on top, business logic and persistence. And I don't know where this comes from. I have two possible scenarios. The first one is that you sure know the ISO-OSI model of network communication, where you have at the bottom layer the wire, and then there's somewhere TCP and IP. And that's just the extension into the software. Then you have persistence, business logic, and UI. That's one possible reason. And the other one is that, yeah, we had some UI developers, some backend developers, and some database administrators. I don't know. Anyway, there are also two ways of layering. You can have strict layering and non-strict layering. There are different rules what you can access. And as always in architecture, it's a trade-off. Strict is simpler, but you possibly have to do a lot of pass-through code because you are only allowed to access the layer one level down. With non-strict, you can access everything below, but yeah, you can access everything below. That can be a big problem. And yeah, when I started writing business software, that was the thing. We just wrote layers above layers above layers. You see a little bit of gray hair, so it was 1 or 2 months ago. So, but this one has a problem. And I've seen that in every team I've been, is that when you can access the persistency code from any layer, you have persistency code in every layer. So yeah, you have persistency in the code behind files of your web framework and so on. So somebody came along and said, yeah, that's stupid that everything can access the persistency layer. So let's switch things around. Let's put the persistency logic on top. And one of the first was Alistair Cockburn, and invented the ports and adapter architecture pattern, or also known as hexagonal, because the first drawing was a hexagon. And here the idea is that in the middle, not above or below, but in the middle you have the application, the business logic. And the business logic knows nothing about its surroundings. So when you are a user and you want to interact with that application, you have to go through a port. So a port is like an interface or a contract. The application states what is possible to be called. And if you're a user, you need a user interface, which is an adapter to call that port. Maybe there is another system that wants to interact with our application. It has its own port. And if our application wants to do something in the file system or a database, it goes through a port with a specific adapter for the technology and does whatever it has to do. The nice thing is that we can switch adapters. For example, if I want to test something, I can use a test adapter or just a test, which is in itself an adapter, and I can swap the database, the real database adapter, with a simulation or a fake or a test double or whatever, and then I get easy testability. So that's the big thing of hexagonal or ports and adapters. And by the way, if you invent something, there are some young people here, if you invent something, please give it only one name, not two. It's really confusing, especially if hexagonal, because there are no hexagons in hexagonal architecture. So, but still we have a problem. So you have this nice insight business logic that knows nothing about the surroundings. You have all these adapters, but your application grows bigger and bigger and bigger, and you can still have a mess in the inside. Because ports and adapters says nothing about how to structure the inside. And in 2008, Jeffrey Palermo came along and said, he wrote some blog posts about how they structure their code. And he called it onion architecture, because the layers are concentric circles and look a bit like an onion skins. And he said that, yes, we have the same idea. In the middle is the business logic, the yellow parts. On the outside are the infrastructure parts, like access to the database, talking to other services, the user interface, or tests. And he split the inner part into three layers: the application services, the domain services, and the domain model. So back then, big enterprises, you had a shared model between different teams, different applications. This was the big domain model, and you wrote your own application services for your own application. And he states that the main premise is that it controls coupling. The fundamental rule is that all code can depend on layers more central, but code cannot depend on layers further out from the core. So all the dependencies, the static dependencies, point only inwards, never outwards. You can know things in the same layer, but not things further out. So the application services can know the domain service can know the domain model, but not vice versa. And to achieve a running system, we need to inject things into the core. So if a domain service needs to load some data, it defines an interface, which is implemented in the infrastructure on the outside and injected into the core. That's why dependency inversion is a basic principle here. And if you want to know, if you have an onion architecture, these are the 4 rules. So the first rule is that the application is built around an independent object model that makes it easy to test. Inner layers define interfaces, outer layers implement these interfaces, just as I explained earlier. Direction of coupling is towards the center. Dependencies only point inwards. And you can, all application core code can be compiled and run separate from infrastructure, which again, is, in my opinion, is the same as the first tenet, but yeah, it makes it easy to test. And maybe you think now, I know these rules, but I don't know that picture. That's probably because you know this picture. Clean Architecture by Robert Martin. Because Robert Martin in 2012 said, yeah, there are a couple of ideas around in the architectural space, and they all look similar. And he distilled from all this idea his clean architecture. And yeah, it looks awfully the same as the onion architecture, but he uses more generic terms to describe the different layers. And there is no rule that you have to have 4 layers. You can have 3 or 5 or whatever. These are just example namings here. But what is the same as in onion is the static dependencies only are allowed to point inwards. And he added in the diagram an example of the control flow. When a user clicks a button, we go to the controller. Then the controller calls a use case. The use case may load some data from the database through an interface that is implemented in the outside, gets some data back, gets the entities, executes some business rules, may call a third-party service, may store some data, and then return a result through the presenter to the user. So the control flow can jump in and out and in and out. That's no problem. The dependency rule is just about static dependencies. He also added what data should cross the boundary between the layers. And he said it should just be simple data structures. Or as I would say, just data. No domain model thingies, just data. And this data should be in a way most convenient for the inner layer. That's obvious because if an inner layer knows nothing about the outer layers, so you can't optimize for outer layers. So optimize it for yourself, for the inner layer. But we still have some problems. And my biggest problem with clean architecture is when you read the initial post, it states that in the use cases section, I have to read it by word, we do not expect changes in this layer to affect the entities. So when we change a use case, we don't expect a change in the entities, in the innermost layer. And in my experience, how we develop software nowadays, that's simply not true. It may have been true back in 2012, but I doubt it. But nowadays, when you build a system feature by feature, or user story by user story, or task by task, or whatever you want to call that, we build the entities together with the use cases. I would say that's the modern way we develop software. So with almost every use case, we have to adapt the entities. So with every change, we have to change most of the layers. And that's not really nice. It's a lot of code to change. And another problem still is, now we have 3, 4, or 5 layers, but you just still don't know how to organize stuff in a single layer. So if you have 1 million lines of code, and let's say there is 250,000 lines per layer, still a lot of code in one bucket. So of course you can organize it, but there is no recipe in this architecture pattern. And some years later, someone, Jimmy Bogart, came along and said, we shouldn't organize things in horizontal layers. We should organize things in vertical slices. Every slice is a feature. We organize code by feature. All the code for a single feature is close together. Because when you add a feature, we just add a slide. If you change some slice, all the code is close by. It makes it much easier to work feature by feature. And he gives in his initial blog post 4 examples of slices. And yes, it's vertical slices, although they are shown horizontally. But yeah, it's his slide, not mine. So one example is get orders. He said, I use some object relational mapper and automapper because that's his library. and I use a DTO to communicate the data back to the caller. That's how I implement the getOrder slice. The getOrder detail slice, he just executes some raw SQL on the database, puts the data back into a DTO, returns it to the client. The approve invoice command, that is important. We should keep the history, so that's why we use event sourcing. I don't know why he would use an aggregate route, but of care. He obviously wants to have some consistency there. And the cancel order slice just calls store procedures because they're fun, or why he calls it why not. So you see, there is no single architectural guideline or rule how a single slice should be implemented. Make the simplest possible thing per slice. And when you do that, as Jimmy Bogart observed, most abstractions melt away. So the thousands of interfaces that only have one implementation and the many code classes and methods that we typically have in clean architecture, they just vanish because you do the simplest thing per slice. Start simple, add something when you need something. Add an abstraction when you really need it, not just because it was written in some blog post. And the nice thing is we can write our system slice per slice per slice or feature by feature. That matches at least how we build our system. But we still have a problem, because if you have a big application, you obviously have a lot of features, and when you have a slice per feature, you obviously have a lot of slices. And when you have a pot of 1,000 slices, yeah, that's not easy to navigate. That's not really understandable. So, for the rest of the talk, I want to show you how we organize things in our application. And it's not meant as a recipe for you, do the same thing and be successful. It's just for your inspiration. Do whatever is meaningful in your situation. But now we have to do a little detour. Mark Seaman coined the term fractal architecture, and he ended with that because he states that we read much more code than we write. For every line of code you write, we read 10 lines of code. Actually, I would be really interested if this is true or not. I think it really depends on the code you're currently writing, but let's go with that. So, if this is true, we should optimize our code for readability. It doesn't matter much how long you need to write the line of code, it matters much more how fast you can read your code base. I would also include how easy it is to navigate your code base, so that you find the code you want to read. And our brains, they are sadly very limited. So our working memory is at max capable of keeping 7 things in the working memory at a time. Maximum. Most people are at 5. A lot of people are at 4. So it's a really, really low number. Working memory, not in your brain, but in your working memory. And if you are capable of keeping 7 things and there is an 8th thing, you have to swap something out. And then you have to swap it back in, and that's really hard work for our memory. So, but here it's not called things, it's called a chunk. So I have to explain what a chunk is. So I assume you know a curly braces language, like Java or C# or C++. So then you know an if statement. So if you are used to an if statement, the whole if statement is a single chunk, because you see, it's an if, it's obvious how it works. But when you see an if statement for the very, very first time in your life, you see, there is this if keyword, then there is a condition, then obviously there has to be some braces, and there is a body. So the first time you've seen an if statement, you probably had 4 chunks, not 1. But with getting used to if statements, the chunk grew bigger. So I'm also an F# developer, it's the F# sign here, and we use a lot of folds. If you're Java programmer, think of reduce in Java streams. If you're a C# developer, think of aggregate in LINQ. That's a fold in F# or in functional programming languages. And if you look at that and you're not used to that, so whoa, that's some crazy syntax, but for me it's just one chunk because that's just how we write code every day. But if you're not used to it, you probably have a lot more chunks. You have, okay, I have a list of values, then I have this crazy pipe symbol, then I have the list fold keyword, then I have a function or lambda that states how things have to be aggregated, and then I have an initial value. So chunks are really personal, and they grow over time. And that's the reason why it's so hard to learn a programming language that uses a completely different syntax. Because you start at extremely small chunks again. So, I'm a software architect, and we software architects, we draw boxes. So, this is my application box. And if I apply this rule of max 7 things, I say, okay, I have to know the system, so I can put at max 6 things in it. So, there are 7 things in total. So, I have a system, I decompose it into 6 parts. And now, because it's fractal, we do that again. Every part consists at most of 6 or 7 things. And because this is self-similar, that's a fractal. Hence, a fractal architecture. And I've stolen some slides from Mark Seaman, but I linked them. That's his talk. So if you're interested in that idea more, you can watch his talk or buy his book. And he gives an example. Can you see that? It's his slide, so I'm not the reason for the bad contrast. And here it's about restaurant reservations. And that's C# code. And he shows here the data persistency code, and he enumerates his chunks. It's important. These are his chunks, not our chunks. We may have different chunks. That's okay. He says the 2 arguments, restaurant ID and reservation, are chunks. Then he does some null checking. That is a chunk. He has to create a connection to the database. He has to create the command, and he has to add some parameters. 6 chunks, perfect method, not more than 7. I would say executing the queries maybe chunk 2, but not for him, obviously. Another one is a little higher up in the abstraction, is where he configures all the services. He has an argument again, it's the first chunk. He does some URL signing key things. He adds controllers and options to services, and he counts again. And with the JSON serialization, he ends up again with 6 chunks. Perfect method. And on the topmost, he has the program that builds everything together, and here says, I just have to start up. I doubt that. You see the code the first time. I think you have more chunks than just one startup, but that's what he said. So, do you know what chunks are now? Yeah. So, now, what did we do with all these ideas, of all these different architecture patterns? In our application. Our application is called TimeRocket, and it's an application for attendance time tracking and a little bit more. And on the topmost level, we say that TimeRocket consists of these subsystems, of these top slices. We call them subsystems so that we have different names, because we will have slices in slices in slices, and that's an overuse of the word slice. So these are subsystems. Our system has the subsystem employment, because he needs to know who works at the company, under which contract. Do you have a monthly salary, or do you work by hour? We have attendance, when do you come to work, when do you leave for lunch, and so on. Absence, when you're sick or go on vacation. Duty planning, to plan your duties. Undertakings, fancy word for projects, because you can track project time or anything else that has some relevance with time. That's why it's called an undertaking. There are expenses. Accounting is the place where we crunch all the numbers together so that we know how many hours you still have to work today or how many vacation days you still have this year. And we have cost centers, so I'm in the development cost centers, and sometimes I work for the marketing cost centers or for internal billing. We have a lot of automation because that's the key selling point of our application, because we automate all the things that are possible. And of course, there is a lot of customization to customize the application to the customer's needs. So, and these are the top slices, and when you zoom in, for example, into the undertaking slice, we see, yeah, slices again. Smaller slices. If you want to use project time tracking, you have to define a structure. What is the thing you are tracking? Are you tracking customers, orders, projects, or whatever? You can group them. There are permissions. There are the actual projects. There are multi-actions, fancy thing, because sometimes people work on multiple projects at the same time, especially when they use machines. So you can track time onto multiple projects at once. And there are activities. These are the actual things you work on. So I hold a presentation from 2 to 3 today. That's my activity. There are budgets, and of course, there are a lot of settings. And when you go in again into the activities, we see we have manual activities, we have multi-action activities, and we have activities from attendance. That's when you say, I always work on the project, just track all my attendance time onto that project. And then we can go in again, manual activities, and see, you can create them, you can replace them, and you can delete them. So, and our whole application is structured in this way, slices in slices in slices, with roughly at most 7 things on every level. So sometimes it's a little more, but it's manageable. So now finally, I can explain to you where we store. Did I really miss to mention that when you explained vertical slices architecture? Yes, I missed that, so I have to do that now. When you have vertical slices, the problem is, where do you put all the shared code? Because when you create a customer and change something on the customer, you probably have shared code. Like, what actually is a customer? Probably some validation logic, maybe some authentication logic. Are you allowed to edit that customer or change it? So where do you put that shared code? And Jimmy Bogart's answer is, as far as I know, a team that knows refactoring will find a way. Certainly true, but I want to show you our way so that you see at least one way how you can deal with shared code. And if you do these slices in slices in slices, the answer is rather obvious. So when we look at create activities and replace activities, when they share something, we just put it in the slice one level up, closest to where the code is that it needs the code. And if manual activity and multi-actions share something, okay, we just put the shared code one level up. We can also take a look at how our application looks at through layers. So yeah, concentric layers, so it must be onion or clean architecture. So when we, again, want to create an activity, we first hit the backend with the activities controller. So I'm a .NET person, we have ASP.NET controllers, and the controller deserializes the request and calls a so-called facade, the activities features facade. We use facades because our code is either hosted in a web service on Azure or is called by Azure Functions. It's like AWS Lambdas. Because we have 2 different hosts, we need a common interface, a common contract that we can call, and that's that facade here. And the facade more or less just calls directly the feature, the functionality you want to execute, to create manual activity here, which, yeah, is F# is just a function. And then the activity, the feature, needs some data. So it calls a persistency function, which it gets through dependency injection, like in clean or onion architecture, builds up its model of the activity, does some validation through calling some shardcode, does its thing, and returns whether it could successfully create the activity or not. So we see we do onion and clean, just a little bit different. One thing we noticed is that there is not a one-to-one relationship of slices between the different layers. So when you start in the outermost layer, the infrastructure, here shown at the bottom, and I call this activities controller, it does not only call the function to really write the activity in the database, it also calls into the audit trail slice. We store that something has happened and who executed that operation for the audit trail. It also makes a call into the authorization code. Are you actually allowed to do that? It also called into the authentication code. Are you really the person you say you are? So typically you call multiple slices in an inner layer, and that repeats for the other layers. When we create an activity for today, we also have to call or trigger the validation logic, is your day still valid? Because our system tracks whether you have a meaningful working day or not. So if you just come to work and never leave, then something is wrong. So we detect such things, so we have to trigger that. And so that's a nice combination of layers and slices. We have slices per layer, and they don't have to match one-to-one. And I think that's the main discrepancy to how Jimmy Boker talks about vertical slice, because he has just vertical slices. And in my opinion, that can't work in a bigger system. But yeah. Then if you look at the solution explorer in our IDE, you see the slices again. Slices are just solution folders, how they're called in Rider or Visual Studio. I don't know how they're called in IntelliJ. My last line of Java was over 20 years ago. But you see the same slices here with the folders, and there are some more, like the composition folder, the second from the top. That's just the code that we use to build up our systems. The composition root builds everything together. And there is also some archaeology possible, because the core folder, that's just the code we wrote 10 to 8 years ago, just one project that is sliced inside the project, but not yet really up to what I explained in this presentation. And there is the fundamentals. That's just the globally shared stuff that all the subsystems can use. And if you zoom into a single folder, for example, the undertakings slice here, you see we have the layers, API and core, and the core is then again layered inside. But that's like in hexagonal architecture, the API, there are the adapters, and the core, that's the core of the hexagon, the business logic. And if we go in one step further and look into these two projects, we see that the API's controllers use the same slicing names as I've shown through this presentation, and the same is for the core undertakings. Now, because it's F#, F# has something very special, that you can only ever reference things that were defined above. So that's really nice, because you can see the layers in the code. So the reason why the facade is at the bottom, because the facade is the code that knows all the other stuff, so it has to be at the bottom. It's the outermost layer in the core, in the business logic. And the facade uses the features, where all the use cases are in there. And above the features, there are all the models, the core, what it's called entities in clean architecture, or the domain model in onion architecture. You see the structure directly in code. So let's zoom in again into the activities. We zoom in into activities models and into the activities features. And you see, again, we have these manual activities, multi-action activities, and activities from attendance. And you see that we share some code there, like the storage and some authorization. But I guess that's better shown here. Zoom in again, and now we are at the deepest level. We see that manual activities are the model for the manual activity and the model for the events, because we are event sourced. And then you see there's a lot of shared stuff going on, like the activity time tracking errors at the top. That's a discriminated union that describes everything that can go wrong. So we don't use exceptions, we use a discriminated union, like an enum on steroids, if you don't know the term. So that's one thing that is shared over everything. And you have the activity storages, because for performance reasons, we have to read all different kind of activities at once, not separately. We can read that all with one query. So we can't split that code up. That's why it is shared. And further down, typically there is a lot of validation logic that we can share. And again, the queries, because the queries use the storage, they can't be split up and are shared. So, now I've talked for, how long did I talk? Almost 40 minutes. I said we have a big black box, and yet now we have really, really nice slices in there and some layers. But that's just the backend. So we also have a UI and the database. And doesn't that look like the first image with the 3 layers? So I guess we didn't get that far in this 40 minutes. It's still 3 layers. Yeah, that's true. But at least we can use the same concept in the user interface and in the database. So we can, of course, use slicing in the user interface as well. But there it gets a little bit trickier, because often in the UI you have to show data from multiple sources together. It's an aggregate view. So it's always a composite UI, where the slicing in the UI is different than the slicing in the backend. Because sometimes you have to show things from 2 slices in the same place. Like when I want to create an activity, I have to tell the system, do I want to create a normal manual activity, or do I want to create a multi-action activity? And that's in the same UI. So the slicing is different. And I can also use slicing in the database. That's called schemas. So we use a schema per subsystem of the backend, just to keep the data separated and easy to find. Yeah. To sum up, I've shown you that we use all the fancy things, like layers. We split things back hand. We have a layer for the controller stuff. We have a layer for the features. We have a layer for the models, the business logic. We have onion and clean architecture, because we inject things to get data from the database, or call other services, or make telemetry, or send notifications. We use the ideas from Fractal Architecture. We have slices within slices within slices. And we use Hexagonal. We use adapters, like the controllers are adapters. And something that I didn't mention is that when one subsystem has to talk to another subsystem, that goes through an adapter as well. Then, of course, we have vertical slices. We build the system feature per feature. We add a slice. And yeah, the last thing, I mentioned it already, is please take all these ideas, but think for yourself how you can use these ideas in your applications. Thank you. So Now you have to stay and fill the time with questions. No questions? What happened to this? What happened to this? Yeah. Let's go back to that. Yeah, the problem is the subsystems are given by our domain. So we have as many subsystems as thing our application can do. So we are limited there to limit them. But below the first level, it's mostly 7 or less. But yeah, it's not perfect. We try, but yeah, it's anyway between 4 and 7. So and only 4 things in a thing, you get a lot of levels, and it's not really that much better. It's okay? Another question? How does event modeling relate to that architecture? I'm not really an event modeling expert, so it's hard to answer that question, but I would say event modeling is more about discovering the domain, what is actually in the domain, and not how we structure things. But that might be wrong because I don't know event modeling that well. It's okay? The question is about the user interface, how we deal with the slicing there, whether we do a lot of aggregation in the backend. Yeah, the UI is special anyway. So we started 10 years ago with AngularJS, and our prediction was that after a year we will rewrite the UI because the technology will change. It took 2 years, then we rewrote it in Angular. And we still thought that, yeah, in 2 years you have to rewrite it, but we're still on Angular now. So we didn't invest that much thought into how we do things on the client. And because we said, yeah, it's much more likely that we have to rewrite the client, we decided that we do most of the things in the backend. Sometimes we even do just backend calls, so we can do complicated things on the backend because it's easier to test. It's easier to write complicated code in C# or F# than in TypeScript. So we do most things in the backend. But that's what just the decision was made because of the volatility of the UI technology, not really because it's UI or backend. Is this okay? Yep. The question is whether we slice the entities as well. And that's a hard question to answer. As the short one is yes, absolutely. Because we think every use case has to have a model that matches that use case. So we actually have a model per use case. But many use cases are so similar that you can share code. But the thought is always build a model for the use case that fits perfectly, and if it just matches another one, you can share it. But we don't go there and say, yeah, we have a customer, the one customer, and we have one model for a customer, and we use it in all the use cases where customers are involved. No, we just build a model for every single use case, and when we see they are similar, or when you see they are the same, then we use shared code. So there is not one big domain model in our application. We have many models. Small models, easy models. It's okay? So we have to stop. If you have further questions, you can come here or talk to me during the conference. I will be around. Thank you.